So we're now looking at graphing polynomial functions. So in this course, we're going to be doing a lot of graphing and some algebra, a lot of algebra that's going to help you when you get into calculus. And being able to recognize a graph and being able to identify important points and things that are going on where it's increasing, decreasing, max, mins, are going to be really helpful when you go further on in mathematics. And probably other topics that relate with mathematics and use it. So these are polynomials. We're going to talk about polynomials and graphing them. And so first of all, what is a polynomial? So a polynomial can be written in the form of a sub n, x raised to the nth power, plus a sub n minus 1, so that sub is just a subscript of little cases, of x raised to the n minus 1 power, plus a sub n minus 2, x raised to the n minus 2 power, plus, so it can keep on going in this form, plus a sub 2x squared, plus a sub 1 times x, plus a sub 0. Okay, so it doesn't look pretty, but basically all it's saying is, first of all, these a sub I terms, these are our coefficients. Our value of n, how can I express this? Let me just grab this really quick. And how they write it. Okay, yeah. So they write it more like a sub 1, that's a sub n like I had done up here. So I'm going to just say, and sometimes I've seen this before, that I is between and including 0 and n. N has to be greater than or equal to 0 and is an integer. We say that n is the degree of the polynomial. And it's an a sub n. We're going to use this when graphing. This is called our leading coefficient. And the a sub 0 value, the one that doesn't have the x attached to it, this is our constant. And this is, if we want to, not as an expression, as a function, f of x is equal to this. The domain of f of x, so those are the values that we can plug in for x and not have any trouble spots. Well, if this is a polynomial, and we'll talk about this more in a minute, and those exponents here are integers, so they can't have a fraction of, so it can't be like 3/2 or 1/2. It can't be 0.2. It has to be an integer. So from 0, 1, 2, 3, 4, up to infinity. And so we're not going to have anything that brings our variables down to the denominator or any radicals. If we had negative exponents, but that can't happen because n has to be greater than or equal to 0, then that would bring variables down to the denominator, and we can't have that in order to be a polynomial. So the domain of f of x is all real numbers. So this is just kind of a generic way to state what a polynomial is. Again, so you've been working with these before. It's just now that we have these variables representing different things. So the number here, this a sub n, x to the n is the largest power. Usually we'll write polynomials, but it doesn't have to be, from highest power descending to lowest power. And that's going to be helpful for us when we're rewriting things in order to graph. Let's see. What else can I tell you? A sub n, this leading coefficient, so it has to be the term in front of the x raised to the highest power. This is also going to help us, both this and the degree is going to help us with the end behavior. So what's happening to our graph as x is going off to positive infinity? Is that graph shooting up to positive infinity, or is that graph shooting down to negative infinity? Or as we're going through, as x is going to negative infinity, going to our left, is that graph going to shoot down to negative infinity or up to positive infinity? And so those values are going to help us with our graph. But certain things that you need to know about polynomial functions, and they always have these characteristics, are that polynomials, and you'll get more and be able to prove this more in mathematical terms, but they're always continuous, which means there's no jumps in our graph, and they're always smooth. So that means that there's no sharp corners in the graph. And so we're going to just write it in layman's terms. So polynomials, the graphs, or graphs of polynomials, are always continuous and smooth. So we're going to be graphing soon rational functions, and we'll see that those are not continuous all the time, and that there's sometimes jumps in our graph, values where our x is not defined. And so this is no jumps, no asymptotes. And we'll talk about asymptotes later, hopefully today. And no sharp, yeah, that's all I think. Oh yeah, no open circles. And that smooth piece, no sharp corners. So the absolute value function, it looks like a v. That is not a polynomial function. And if you saw the graph, you should be able to recognize, does that look like if the polynomial could represent it or not? So jumps, just kind of look at it. This could be something like here where we were graphing piecewise functions. And so one piece you graphed, and then the domain changed, and then you graphed another piece. So this would not be a polynomial function because of the jump in the graph. We saw when we were graphing 1 over x that x was not defined. We also saw, and I talked about, well, there's this vertical asymptote here and a horizontal asymptote here. So it really depends on, so this right here is an asymptote. So this can't be a polynomial function. Open circle. So it could look like it's smooth and continuous until maybe one point. open circle, and then goes on. So these are all examples of things that are not polynomials. Okay, so determine which functions are polynomial functions. For those that are, state the degree. For those that are not, state why not. Write each polynomial in standard form, then identify the leading term and the constant term. Okay, so we're asking ourselves, is this a function? Why or why not? If so, what's the degree? Put in standard form. And identify the leading term and constant term. Okay, so a lot of mathematics is a lot of terminology, and so if you don't understand what certain things are, you get lost. Like, what does it mean to be a term? So if we're looking at our polynomial here, all of our terms are always split up between pluses and minuses. So a sub n, x to the n is considered a term. A sub 0 over here is considered a term. A sub 1x, etc. Okay, so looking at the following, let's put, I'm going to write this down all the time. What if we had f of x is equal to 5x squared plus 4x to the fourth? Okay, so looking at this, does it follow all the things that had to hold true? Are the degrees or the exponents, are those positive integers? And they are. And so, and we don't have any like variables in the exponent, or I'm sorry, in the denominator or exponent, I guess. And so this is a polynomial. It's not written in standard form. We could rewrite this in standard form, right? And rewriting it in standard form, we would rewrite it with a term with the largest power descending in powers. Well, there's only two terms. So 4x to the fourth plus 5x squared. So we now have it in standard form. The leading term oops, I also forgot the degree. Well, the leading term is equal to 4x to the fourth. If I wanted to identify the degree, that's always the highest exponent of your polynomial. Well, the highest exponent value is 4, so the degree is 4. And the leading coefficient, because we'll be talking about leading coefficient, it's helpful to identify if it's positive or negative when we're looking at graphs. But our leading coefficient is just the number in front of the variable raised to the highest power. And so in this case, it's 4, and it's a positive number. Identifying if our degree of our polynomials, even and odd, is also going to help us with our graph. And so this is an even degree. And then our constant, that also helps us when we graph, because when because for polynomials, when you're plugging in 0 for x to find your y-intercept, it's always going to equal to the constant. So looking at this, there's no term that we're adding to our polynomial that is not attached to x. So we can think of our constant, if we want to, as 0. If we put plus 0 here, it'd be the same exact thing. Okay, so same questions. What if you had g of x is equal to the square root of x all times the square root of x minus 1? Do you guys believe that is a polynomial or not a polynomial? Why or why not? So I'll throw that out to you guys. So by definition, is it holding true? Anyone know how we can rewrite a radical as an exponent? So that's something also that you're going to use all the time in calculus, being able to go back and forth between radicals and the exponential form. Also, rules of exponents are useful. Yeah.
I was just saying in that case, then the square root of x is x to the 1/2.
Right. And so we could rewrite this as x to the 1/2 all times x to the 1/2 minus 1. So is that a polynomial? Okay, so I'm getting that. So let's look at this just for, normally you don't have to distribute. I can tell that it's not, but let's just distribute and remember rules of exponents. So if you distribute, you have the same base here, x. Remember we add our exponents, so 1/2 plus 1/2. And I have to also distribute this to my -1, so minus x to the 1/2. But if I add 1/2 plus 1/2, I get x to the first power, which you normally won't write that 1. So right there, that holds true that it's an integer and it's positive. But not right here. This is not an integer. And so I could write it like this again. But no, so this is right. And some of you guys were saying it in the chat. So the exponent is not an integer. And I probably should say positive integer. So what about h of x is equal to 5x to the 4th minus pi x cubed plus 1/2. And this one, a polynomial. What do you guys think on that one? So we're seeing if it holds true. So our variables, are they raised to positive integers? So the fourth power, that's positive. Third power, that's positive. And they're both integers, so we're good there. So pi, I mean 5 and 1/2, those are all real numbers. But we'll actually work with things that have complex numbers or imaginary numbers later. Okay. So yes, this is a polynomial. It's already written in descending order of powers. The degree is, so you should be able to identify the degree, the leading term, leading coefficient, and the constant. So what's the degree of that one? All right, so degree 4. And the leading term is it hard to type that one? All right, so 5x to the 4th. The leading coefficient right, it's 5, and the constant is, you're on a roll, so 1/2.
I have a question.
Yeah.
How do you determine the leading term? Is that always just the biggest number? Okay.
So the leading term is always the term that has the degree to the highest power. And so degree 4, and so it's a term with the degree that shows you the degree. And so it's going to be 5x to the 4th. The leading coefficient is just the number in front of that variable raised to the highest power.
Okay, makes sense. Thank you.
Mm-hmm. Okay, so one more. What about capital G of x? And this is defined as 2 all times x minus 1 quantity squared all times x squared plus 1. So same questions. First question is, does this represent a polynomial? So what do you guys think? So you can all do thumbs up or thumbs down. Thumbs up if you think it's a polynomial, thumbs down if you don't. How do we find that thumbs up, thumbs down? Awesome. Can you guys see other people's thumbs ups? Just curious. Yeah, so you guys are right. So I don't know if seeing everybody going, if you follow the crowd or if you actually knew that. But yes, you are right. It is a polynomial, actually, and it's in a great form because we can tell what the intercepts are in this form. And we're in a great form and where we can tell what's happening at those x-intercepts. And we'll talk about that in a minute about multiplicity. But it's also in a form you should be able to identify what the degree is without multiplying that all out, because that could be a lot of work. So thinking about that, if you had gone through all the work and you had distributed and combined like terms, what do you think the degree, what is the variable going to be raised to? Highest power. Okay, so I think Natalie actually answered it, but I'm not sure if that was from the last question or not. But so degree 4 is correct. And we can think about it logically. If we had distribute out x minus 1 times x minus 1, when we FOILed that out, the highest degree would be x squared. And then when we multiply this x squared times this x squared in the second parentheses, well, x squared times x squared is x to the 4, so the degree is 4. And maybe that helped you with the next question is what would the leading term be if you had went through all the work to distribute that out? But you didn't, right? So 2x to the 4th. So the leading coefficient so if you distribute all that out, the leading coefficient, so that's the number in front of the variable, reach that highest power, right, is 2. And then one more question, what do you think about the constant? What would we get back for the constant? Yeah, so 2 is correct. Because when we FOILed this out, x minus 1 times x minus 1, that coefficient, or that constant was plus 1 in there, times this 2 is 2, times this 1 is 2. Okay. Okay, so let me see if what they call it. Again, that this is different text that I normally teach out of. They don't call it anything. Oh, theorem and behavior of the graph of a polynomial function. Okay, so this is always true according to this theorem. If the conditions hold true, you have a polynomial function, then you can find the end behaviors of the polynomial function. And it's by using the leading term. Okay, so determine the leading term. Which in our form when we wrote it was a sub n x raised to the nth power. Okay. And then we need to determine, is a sub n positive or negative? And we need to look at if our degree n is it even or odd? Okay, so depending on those conditions depends on what's going to happen to our graph as we go to positive or negative infinity. And so let's kind of make a table here. We have our a sub n value, and it either can be positive or it can be negative. We have our degree. So n, this degree, this is either positive, I'm sorry, not positive, even or odd. Okay, so I'm going to show you with an example. So let's look at an example where we have a positive coefficient in front and an even power. And so if that's the case, so positive number, I don't know, 2 is positive number, and x raised to the second power, that's positive. I could even go to any, I'm sorry, not positive, it's even. It's also positive. So I could go any degree I wanted to. That was even. X to the 12th power works. And so we're trying to look at, and I'm going to give you kind of notation and I'll explain what it's saying in a second. So we're looking at LIM and x is going to negative infinity of f of x. So this is saying what is happening to your y value which is f of x as x goes to negative infinity. Okay, well, let's just think about it logically. If you throw in, if it's going to negative infinity, that just tells me that I'm plugging in negative numbers that are, the absolute value of them are getting larger and larger. So if we go in and we plug in a negative number wherever we see an x and f of x. And so doing that, we have, this would equal 2, I see an x there, I'm going to plug in a negative number, raise it to the 12th. Well, if you raise a negative number to a even power, is the result going to be positive or negative at the end? So it's the same thing, basically, if you want to think about it this way. We could raise the negative piece to the even power, the -1, raise the 12th power, and we can raise the number to the 12th power. Basically, this is going to equal, I want to get at it, is a positive number. I don't know care what positive number is, but I know it's going to be a positive number. And so basically, and as that number is getting, this number is getting the absolute value of that is getting larger, this is going to be blowing up. And so our end behaviors, when you have a positive coefficient, as x goes to negative infinity, you're going to see that your graph is going upwards at the end. We don't know what's going on in here, and we'll talk about what can be going on in here in a minute, but we're just trying to figure out what's happening at the ends. Behavior. And so we also want to now look at what's going on with x as x is going to positive infinity. And so basically we're looking at the limit. That's basically the terminology, and it's written as LIM, as x, an arrow, and then an infinity of f of x. So we're looking at what happens to y, or f of x, as x goes to positive infinity. So this time, instead of plugging in a negative number, you're plugging in a positive number. Wherever you see an x in your function, well, actually, in this case, we're only looking at the leading term. It doesn't matter what anything else was. Well, if you raise a positive number to the 12th power, that's positive, and times our 2 out front, which is a positive number. So this is equal to positive, or 2 times a positive, which is positive. So over here, that limit as x goes to negative infinity of f of x, this was infinity. And the limit as x goes to infinity of f of x is equal also positive infinity. And so our graph, as x goes to positive infinity, shoots upwards. Okay, so looking at all these different case scenarios, so positive and an odd number, odd degree, sorry. So if a sub n, x sub n, let's say a sub n is positive, so greater than 0, and n is odd. So if we're looking at the limit as x goes to negative infinity of our polynomial f of x. So basically you have a positive number because our coefficient is positive. Now think about it. If you raise a negative number to an odd power, this is equal to a negative number. So really, and I'm just worried about the sign, what I'm getting back, positive or negatives for my y value. As x is going to a negative infinity, when I'm plugging those values in, my graph is going to be negative, and so it's going to be shooting downwards. So same kind of reasoning, I can think about it when I'm plugging in positive numbers, and for x. We'll have a positive coefficient out front. So limit as x goes to infinity. I have that positive coefficient up front, and I'm taking a positive number, raising it to an even power. Well, any positive number raised to any power is always positive. And so I have a positive times a positive, which also gives me back a positive. And so that tells me as x is going to positive infinity, as x gets bigger and bigger and bigger, my y value also gets bigger and bigger and bigger. So it's shooting upwards. Okay, so we are looking next at negative coefficient, even degree. So we have a sub n, x to the nth, where a sub n is less than 0, it's a negative number, and n is even. So if we look at the limit as x is going to negative infinity, well, we have a negative number, it's a negative coefficient out front. And then we're taking a negative number and raising it to an even power. So exponents come first before multiplication. So negative number raised to an even power. Well, that's going to end up becoming positive. So we have a negative times a positive, which ends up being a negative number. So graphically, as x goes to negative infinity, gets smaller and smaller and smaller, so does our y value. And so do the same thing now when x is going to positive infinity. So limit as x goes to positive infinity of f of x. So negative coefficient in front still, because it's less than 0, and positive number that we're plugging in for x, raise it to an even power. So this is equal to a negative times a positive, which is also negative. So it's shooting downwards, going to negative infinity as x goes to positive infinity. And then one more case scenario is when you have a leading coefficient that's negative and an odd degree. Okay, so if we're looking at a sub n, x to the n, where a sub n is negative, less than 0, and n is odd. So if we're going to negative infinity, you have a negative number out front. You're taking a negative number, raising it to an odd power, so multiplying it an odd number of times is also going to give you a negative number. So you have a negative still up front times a negative, which gives us a positive. Before we go up there, let's just do x goes to positive infinity at the same time. So we have a negative coefficient out front. We're taking a positive number and raising it to an odd power. Well, any positive number raised to any power is positive. So we have a negative times a positive, which is negative. Okay, so as x goes to negative infinity, we're shooting upwards, and as x is going to positive infinity, we're shooting downwards. So a couple characteristics that you might notice if you looked at this a little longer, and that the end behaviors Notice that even degrees, look at the end behaviors. When it has a positive coefficient, they both go upwards. And when it has a negative coefficient in front, they both go downwards. So if it's an even degree polynomial, notice that the end behaviors are going in the same direction. So we could look at a graph of a polynomial function, not know what the equation is, but we could determine that it is an even degree by just looking at the end behaviors. With odd, notice that the end behaviors of the graph are going in opposite directions. I was going to tell you. Because another thing that's true about polynomials are all polynomial functions can be rewritten in terms of linear and or quadratic. How about instead of just saying quadratic, let's say irreducible. Quadratic factors. So this irreducible quadratic factor, or quadratic, so irreducible quadratic, what I mean there is if you went to go factor it, or you're trying to find out where it's equal to 0, so your x-intercepts, we're also going to call those different terms that mean the same thing in this chapter, so roots or zeros of your polynomial. If you went to go factor it, you would get an imaginary number. So it's not factorable over the real numbers. So irreducible quadratics cannot be factored with just real numbers. Oops. Okay, so that's kind of cool that we can factor it over the linear and or irreducible quadratics. When it's factored, we can tell a lot about the polynomial. We can tell where it's going to touch or cross the x-axis because we were setting each factor equal to 0 before. Those, if we were looking at polynomial, is where it's going to cross the x-axis. And so let's say, let's do this. If x minus a is a factor of f of x, where f of x is a polynomial, then we say that x equals a is a 0, depending on what book you're looking at, or root of the polynomial. it's also the x-intercept. So they all mean the same thing. Okay, so depending on how many times a factor occurs, so sometimes a factor can occur more than once. For instance, if we had x squared minus 2x plus 1, say f of x is this. We can factor this. F of x is equal to, well, we're thinking of the same two numbers that multiply to give us positive 1, but add to give us negative 2, which is x minus 1 times x minus 1. So x minus 1 is considered to be a factor. It's linear because our degree is 1. So it's factored into two linear equations, but those factors are actually identical. So we could actually rewrite this as x minus 1 quantity squared. So here we would say that if you set this factor equal to 0, well, we're looking at when is x minus 1 equal to 0? If we solve this, this is when x equals 1. So we say that x equals 1 is a 0 of f of x, but we're going to say with multiplicity of 2. And the reason why it's 2 is because if you counted out the number of factors x minus 1 occurs, it is occurring twice. Or if it's written where it's simplified, we can look at the exponent of that factor. And so determining the multiplicity of that 0 tells us actually what's going to happen on the graph when we graph it. So the multiplicity of the 0 represents what happens on the graph. At the x-intercept. Okay. If the multiplicity is even, so basically we're only worried if the multiplicity is even or odd. Does that factor occur an even number of times, or does that factor occur an odd number of times? And so depending on if the multiplicity is even or odd depends on what happens at that graph. So if the multiplicity is odd, the graph crosses the x-axis at the 0. And if the multiplicity is even, the graph just touches the x-axis at that point and turns back around and goes in whatever direction it had come from. So it's either going to come down and hit the x-axis and come back up, or it's going to come up and hit the x-axis and go back down. So the multiplicity is even. The graph just touches the x-axis at that value and does not cross. Okay, so list the real zeros and its multiplicity. Determine whether the graph crosses or touches the x-axis or the x-intercept. Determine the maximum number of turning points on the graph and determine the end behaviors. That is, find the number of function that the graph of f resembles for the large value of x. Okay. They explain a little differently. And I didn't tell you anything about turning points. Let me just tell you about turning points real quick. So the degree of our polynomial actually tells us how many turning points our graph can have. Well, it tells us the maximum number of turning points. So when I mean turning points, it's the number of times that it's going to change directions. So if I'm looking like this, this has 2 turning points. So the degree of the polynomial, so if f of x is a polynomial, and n is the degree of the polynomial, then f of x has at most n minus 1 turning. Points. Let's put it all together. So if you're given f of x is equal to 2 all times x minus 3 all times x squared plus 4 cubed. So list each real zero and its multiplicity. Okay, so it's factored. So we can find the zero by setting each factor equal to 0 and solving for x. Well, the first factor, which is 2, we set that equal to 0. Well, that just doesn't work. X minus 3, looking at when that is equal to 0, well, that's when x equals 3. X squared plus 4, this is quadratic factor because if you went to factor this, it doesn't factor over the real numbers. And we can show that if we were looking at when is, whoops, x squared plus 4 equal to 0. If I subtracted 4 on both sides, or I can use the quadratic formula, but I'm going to use my square root method. So taking the square root of both sides, well, taking the square root of a negative 4 is plus or minus 2i. So this is not real. But later this week, so I might as well just tell you, we're going to be looking for roots that are all types of zeros. And so these would be considered zeros, but they're just not real zeros, real numbers. And so we only have one zero, and it's x equals 3. And the multiplicity, usually I don't think you state it when it's 1, but there's only, that factor only occurs once, x minus 3. So the multiplicity of x equals 3 is 1. So determine whether the graph crosses or touches the x-axis or the x-intercept. So if we were to graph this at x equals 3, is that going to touch it or cross it? So odd multiplicity, it's going to so it crosses the x-axis. So determine the maximum number of turning points on the graph. Well, before we do that, we need to figure out what is going to be our leading term of f of x. Because looking at that, that can tell us what the degree is. That tells us how to determine the end behaviors, depending on if that coefficient is positive or negative, or if our degree is even or odd. So if you had went through and you FOILed and you distribute x squared plus 4 times x squared plus 4 times x squared plus 4, you did that 3 times. Think about that leading term just for distributing that out. So that would give us x to the x squared times x squared is x to the 4th. X to the 4th times x to the 4th is x to the 6th. I'm sorry. That's not what I meant to say. X squared times x squared is x to the 4th, and x to the 4th times x squared is x to the 6th. And x to the 6th times this x is x to the 7th times this 2 here. So leading coefficient, if you went through all the work and distributed that out and combined like terms, which we don't want to do, you would get 2x to the 7th power. And so our degree is equal to 7. And so the number of turning points it's the degree, which is n minus 1. So the maximum number of times that graph is going to turn is 6 times. And so those points where it's turning, those were what we were calling our local extrema. They could be absolute extrema also. So those were the local max and local mins of the graph. Okay. It wanted to know also what the end behaviors of the graph is. And so the end behaviors of our graph didn't matter about anything else about that leading term. And so if we look at the limit as x goes to negative infinity of 2x to the 7th. So if you plug in a negative number that's getting smaller and smaller and smaller, and you raise that to the 7th power, well, that's going to be a negative number. And so we're going to have 2 times a negative number is a negative number. So this is going to shoot down to negative infinity. Just reasoning, we can do it. We know it's an odd, so we also know that it's going to be in opposite directions. But reasoning, taking any positive number, raising it to a power is positive times the coefficient of 2 in front doesn't change the sign of that number, it's still positive. So we can actually tell what's going on a little bit with this graph. And we should be able to graph a general sketch of this. Unfortunately, we are not using graphing calculators, but I want to show you what that looks like. Actually, let's graph it a little bit, and then we can use, and you guys can use this Desmos.com. This has a couple cool features, and it's also would be helpful in calculus. And if you're going to take my calculus class in the fall, this is something we'll be using sometimes when we're looking at limits. But anyways, Desmos.com is a good graphing calculator. I'm sure there's many other ones on the internet that will also work good too. But anyways, okay, so we want to let's look at the graph. Or general graph. That f of x equals to, what was it, x minus 3. X squared plus 4 cubed. Other things that could help us with graphing this is thinking about symmetry, but I don't think it's symmetrical about anything. Only thing we know about x-intercepts is that it's going to be, what was it, positive 3. So I'm going to put a point here. We also know end behaviors. So we know that as x is going to negative infinity, y is going to negative infinity. So I'm going to just show myself that it's going down here. And then as x goes to positive infinity, we're going to go up to positive infinity. Only other thing I know in here is I can figure out the y-intercept by plugging in 0 for x. If I do that, though, I'm going to get some pretty small number. Because if I FOIL out x squared plus 4 times x squared plus 4 times x squared plus 4, it would be 4 times 4 times 4. So 4 cubed is 64 times my negative 3 out front times the 2. And so that gives me y-intercept at negative 384. So f of when x is 0, if I did this right, we get negative 384. So for us, we don't know anything else, and we won't know anything else until we have the tools of calculus. And so we're going to use next semester calculus to be able to help us graph this without having a graphing calculator. Let me show you the graphing calculator feature. I might have a problem. We'll try it because my keyboard's not on, but let's try. Okay, so we're going to use the graphing calculator. And we're going to plug in our equation. And so we were given parentheses. It was x, oops, I'll put it in a second. But it was x minus 3. It was all times x squared. Sorry. If I had my normal keyboard, I would be not as bad. X squared plus 4. And then we're going to cube that. And then I can't forget about this 2 in front. Oh my gosh. Did you see that? I accidentally put erase when I meant to push return. Well, now I'm getting better at this. It might not take me as long. That should be a plus. And that's a square. No, that's a cube, I mean. Something's wrong. There's something wrong here.
You forgot the x squared.
Ah, that's what, I'm like, there's no way. I know it's not crossing more than twice. Thank you. There we go. Let's see if we can get rid of that. I'll zoom. Okay, so right now it kind of just looks like a straight line, right? And we see that it crosses where we're kind of seeing, we were saying it was about 380 something. You can see the x-intercept, which we had found. We saw that said it was crossing. You can see that the end behaviors are going in each direction. I wonder if it can zoom out. And I don't see anything that showing me that it's changing any directions. Oops, here. I don't know. So my guess is that there's no turning points. But without calculus, I really can't tell you that. Okay. So you should get a kind of a general idea, and that was probably not the best one to do. And that was not part of what it was asking us to do there. But we'll look at a different example maybe later. And then, so basically, if you were given a graph and an equation, you should be able to identify which of the graphs, so this one is saying there's multiple, which of them could be a graph of a polynomial function. If so, what are the real zeros, and state the least degree of the polynomial can have for those that cannot say y. Okay, so let's say you have a graph that looks like the following. Okay, so first of all, could this represent a graph of a polynomial function? And so looking at a graph, as long as it's smooth, there's no sharp corners. So there's no sharp corners in here, we're good. And there's no jumps, we're good. And there's no asymptotes, vertical asymptotes, which actually cause jumps. And so this could be a polynomial. So we want to figure out, let's talk about the multiplicity or the zeros. So the zeros of the polynomial well, those are the values where it's either crossing or touching the x-axis. And so we have 3 points where our graph is crossing the x-axis. And so we have the zeros at x equals -2, x equals +2, and x equals 4. They all cross the x-axis. So they have to be odd multiplicity. We also know that and it wants to know, or your question is asking, state the least degree of the polynomial can have. Okay, well then if it's odd multiplicity and we want it to be the least degree, then let's say that this has each multiplicity 1. Right, because if the other odd degree multiplicity would be 3, 5, whatever, then that would give me a higher degree polynomial, and I want to find the least degree polynomial. So degree 1 times the degree 1 times the degree 1, that gives me degree of 3, x times x times x. And so let's just make sure that our end behaviors are good with that. So degree 3, let's see. So narrowing it down, check the end behaviors. Well, odd degrees have different end behaviors. One shoot up, one shoot down. So yes. And then what else do we have to look at? Number of turns. So if you look at the number of turns in here, well, we have one spot here and one spot here. So 1 plus 1, so that's 2 turns. Well, by definition of number of turns, the most number of turns was n minus 1. So in our case, n minus 1 equals 2 to the most number of terms. If we add 1 to both sides, we get n is equal to 3. So the degree of our polynomial that could fit this is degree 3. We could actually even go further, and we could give one polynomial that would work. And this is something else that we would do in this chapter, so we might as well just tie it all together as we're going. And so we could say one polynomial, but there's an infinite number. We can talk about that in a second. Could be f of x equals, well, if negative 2 is a 0, x equals negative 2 is a 0. We talked about this last week. If we added 2 to both sides, x plus 2 is the factor. So x plus 2 is our factor. X plus 2 is a 0. X equals 2. So if we subtract 2 on both sides, so x minus 2 is going to be a factor. And 4 is a 0, and so x minus 4, same reasoning, is a factor. But technically, any coefficient that is positive, I can have in front of here. Any positive number. In here would work. Okay, so let's pause here. So we're looking now at graphing these polynomials, so putting all the pieces that we were just learning together. And so let's say you were given the following. So let's say f of x is equal to x all times x plus 2 quantity squared. So when we're graphing these, we want to find the following kind of information. We want to find the end behaviors of the graph. And it doesn't matter what order we do this. So let's look at that. So we're looking at the limit here as x goes to negative infinity of our graph of f of x. This is the same thing, a limit as x goes to negative infinity of looking at whatever that leading term was. So if we had distributed out x plus 2 times x plus 2, that leading term would be x squared times the x in front. That gives us an x cubed. So if we take a negative number and we cube it, we get back a negative number. And so as x goes to negative infinity, y is also going to negative infinity. So we could also look at the limit as x goes to positive infinity. It's the same thing as looking at the limit of our leading term, which was x cubed. So putting a positive number in there and cubing it, you get back a positive number, and so it's going to go to positive infinity. Also, we can tell the degree is 3, so that should be that our end behaviors are going in opposite directions. They are. You should be able to find your intercepts and state the multiplicity and know what's happening at the x-intercepts, if it's crossing or just touching there. So the x-intercepts so this is when f of x equals 0. It's nice because it's already factored for us. So we're looking at when is x times x plus 2 quantity squared equals 0. So that's when our factor x equals 0 and our factor x plus 2 equals to 0. So we have two x-intercepts, 0 and negative 2. X equals 0 has a multiplicity of 1. And x minus 2 has a multiplicity, well, degree is 2, so of 2. Degree here of x is 1. And so we know at x equals 0, we're going to cross. And at x equals negative 2, we're just going to touch. So we should be able to find our y-intercepts. So y-intercepts occur when our x value is 0. So we're looking at f of 0. F of 0 is equal to, we'll go in and wherever you see an x, you're going to replace it with a parentheses. And rewrite it with 0. And so f of 0 is equal to 0 times 0 plus 2 quantity squared. Well, right away, because of this 0 outside, 0 times anything is 0. So our result is 0. So we have a y-intercept at 0, which makes sense because our x-intercept is also, we have an x-intercept at 0, which is our origin. Okay, so we want to kind of put the pieces together. So we know we have a point at 0. We know we also have at 0, 0. We also know we have a point when x is negative 2. So negative 2, 0. We also know our end behaviors. As x was going to positive infinity, our graph was shooting upwards. And as x was going to negative infinity, our graph was shooting downwards. So we know that this graph has to come up here as it's getting closer and closer to negative 2. We know it has to touch. We also know that it's just touching and it's turning around because of the multiplicity being even. So somewhere in here, we don't know exactly where, it's going to change directions and it's going to come back up. And now we know it's going to cross that x-axis. And so we get a general idea of what the graph looks like. But we don't know particular values like where is this changing direction. And again, that's tools that you'll learn in calculus and you'll be able to find what this minimum value is. You'll also be able to, so that minimum value is where it's changing from decreasing to increasing. So that's where, you would use the Desmos. So some of your homework tells you to use a graphing calculator. None of that stuff will be on the exam, but to help you, you can use the Desmos. So let me see if I can pull it back up. Where's my mouse? Okay. So let's go in and let's rewrite what our function is. And that was just x. Oops. Actually, I don't think I want that. Okay, so we got x all times x plus 2 quantity squared. So looking at our graph, that's not what I want. I want the other way. I wonder if there's a way I can, let me just reset this. Let's do -10 to 10. Oops, shoot. Okay, so that. And so we can see we got that general shape. My y values too, if I change my y values, that's going to help me with, so let's do that real quick. Sorry. So let's change that, and we might have to change a little more. Okay, much better. So that's kind of what we had gotten. If we click on this point where it's a max, absolute max, you'll see that it's at -2, which we had said that it was going to touch there and turn around. See that our end behaviors as x is going to negative infinity is shooting up. This is that where our minimum is going to occur. So you can see that point, it's a special point. And so if MyMathLab asks you, you could put that value in. And then we saw that we had an x and y-intercept at the origin 0, 0, and we also said it was going to cross. We also said as x goes to positive infinity, the graph would be continuing to shoot upwards. So we got a general shape of the graph by the tools that we just learned. Okay. Okay, so another one. What if it had been f of x is equal to 5x all times x squared minus 4 all times x plus 3. Okay, so we want to figure out end behaviors. We want to find our x and our y-intercepts. We want to determine what's happening at the x-intercepts. So we need to determine the multiplicity. And then we can use a graphing technology to help us if we need to determine max and mins. Okay, so first of all, I noticed that f of x is not fully factored. If we look at, because we talked about these could be factored in terms of all linear factors and or quadratic. And so if I look at my quadratic factor, x squared minus 4, I notice that that can be factored further. That's not irreducible over it's not an irreducible quadratic. So it can be reduced over the real numbers. That factors as x minus 2, x plus 2 is the difference of squares. So we have f of x can be rewritten as 5x times x minus 2, x plus 2, all times x plus 3. So we see our zeros. Here are also our x-intercepts. Are at x equals 0, x equals positive 2, x minus 2 is 0 and x is 2, x plus 2 is 0 and x is negative 2, and x plus 3 is 0 and x is negative 3. These all have a multiplicity. None of them repeat themselves as factors. So multiplicity of 1. Oops. So we're going to cross the x-axis at all those values. If we plug in 0, wherever we saw an x in that equation, we can figure out what our y-intercept is. And so doing that, we have, well, I can do the same reason we did last time because of plugging in 0, 5 times 0 is 0, and 0 times anything over here is going to give us 0. Okay, so 0, 0 is a point, which we knew again from above because x equals 0 was also an intercept. So let's determine the leading term. Of f of x, and that would determine the end behaviors of the whole graph of f of x. And so if we had distributed this whole thing out, x times x is an x squared times another x is an x cubed times this 5x out front is a 5x to the 4th. So it's an even degree. Both of our end behaviors are going to be going in the same direction. The coefficient in front is positive. So a positive number, anything raised to a even power is positive. Negative number to an even. So this is going to go to positive infinity. We plug in positive numbers for x, 5x to the fourth, again, it goes to positive infinity. So they're both shooting upwards. Okay, so we have some particular values that are important to graph. So our x-intercepts. So we found that was at 0, 0. At 2, 0. At -2. And at -3. We also knew that our end behaviors were shooting upwards. And we also know that they were crossing our x-axis here. So somewhere in between -3 and -2, it has to turn around to hit that and cross the x-axis again. Somewhere in between -2 and 0, it has to turn around, I don't know where, and hit this x-axis again at 0, 0. It has to cross. So in order to get and hit back at x equals 2, it's going to have to change direction. So you have a general idea of what it should look like. And again, we can find these particular values. We need technology. But notice, so there's 1, 2, 3 turning points. That's one less than our degree of 4. That's the maximum number of turning points. It's possible that this didn't turn as much, but with where our x-intercepts are and what we have, it has to be 3. So let's graph it. B. And so here we have 5 x all times, what do we say? It was x minus 2, x plus 2, because we factored it. X plus 2. And then it would have been x plus 3. Oops. Okay. So it doesn't look very pretty in here. And so I need to, let's make our y values larger, and I can either try it this way. I want you to see both the max and the mins. Whoops. Darn it. Wrong direction. Okay, so if I held my cursor over this point where it's crossing, we should see that that is at -3. So -3, 0. We said that this was going to be -2, which it is. We said that this was going to be 0, 0. We said that this was going to be 2, 0. So all of those were what we said was going to happen. Our end behaviors are both shooting upwards. And then we can, when we knew they were turning directions in here, but we didn't know exactly where, but we can find those values. So this is approximately -2.5 or -2.6 and -14.4. This we can approximate. So we have an absolute, actually this is a local min. This would be a local max. So approximately negative 0.9 and 30.2. We have an absolute min here because this is the lowest value on the whole graph. And notice we don't have any absolute maximum values because both of those graphs on the end behaviors are shooting up forever. Unless we limited the domain, then it has to have an absolute max, absolute min by that extreme value theorem that we talked about. Okay, so let's look at an example where it wasn't given to us in factored form. And then we'll get into the next sections, graphing rational equations. So I might want to change this just because of what we looked at. Yeah. So kind of steeper down here, right? Okay, so let's say you're given f of x. This is equal to, so for each, it says graph each of the polynomial functions. So this is 3x raised to the 6th power plus 6x to the 5th minus 12x to the 4th minus 24x cubed. So from here, we can tell what the degree is. It's 6. We have an even degree, so we know it's going to be shooting both upwards or both downwards. We can see that our leading term is 3x to the 6. So as a limit, as x goes to negative infinity of f of x, that's the same as the limit as our leading term, 3x to the 6. Well, negative number raised to an even power is positive times a positive coefficient out front is positive, so this has to be going to positive infinity. And so, because it's even, they both have to go the same direction or just do it with reasoning and get positive infinity. So Y-intercept, that one's easy when it's in this form. This is when x is equal to 0. So f of 0, all terms have x in it. So when we plug in 0 for x, that's going to go to 0. Okay, so x-intercepts are a little harder here. We're looking at when is f of x equal to 0. So when is this whole thing 3x to the 6 plus 6x to the 5th minus 12x to the 4th minus 24x cubed equal to 0? So we need to factor. First thing what you do when factoring is we're looking at the greatest common factor of all 4, in this case, terms. It says 4 terms. So looking at our numbers in front, 3, 6, -12, and -24, the largest number that divides into all 4 of those numbers is 3. So we can factor out a 3. And then looking at our variables x to the 6th, x to the 5th, x to the 4th, x cubed, they all have x in it. We can pull out an x. The most number of x's they all have in common are 3 of them, so we can pull out an x cubed. So doing that, pulling out 3x cubed, we would be left with an x cubed for the first term, plus taking out 3x cubed from 6x to the 5th, would give us back 2x squared. Oops. 2x squared. Minus, so 3 times what is 12? 4. X cubed times what is x to the 4th? X, another way to think of it. We pulled out a positive 3 from -24, so that would be a -8 here. And x cubed, we pulled out all the x, we pulled out x cubed, so there's no more x's left. Okay, so we want to factor this further. And so right now, we just have the tools that we've looked at in the past. We're going to look at other tools on how to do this later in this chapter, which you probably haven't seen before. But right now we're using the tools that we just know from previous courses. And so number of terms, when you're trying to factor, helps you learn or determine how you're going to factor it. So basically, if it's 2 terms, I know that I'm looking for a difference of squares or a sum or a difference of cubes. If it's 3 terms, I'm looking at a quadratic or quadratic in form, and I'm trying to factor it that way. If it's 4 terms, which this is, then right now factoring by grouping should work. So we want to try factoring by grouping here. So that means I want to group the first 2 terms together, the last 2 terms together, and then pull out what they have in common in each. So let's pull down, because we are, even though we're not using it right now, we need to not forget about this 3x cubed. And so we have 3x cubed all times. Okay, so pulling out what they have in common, x cubed and 2x squared. They both have an x squared in common, so we could pull out an x squared there. And if we pull out an x squared from those first 2 terms, notice that we're left with a single x and plus 2. So go to the last 2 terms inside that big parentheses and look at -4x and -8. What do they both have in common? They both have a -4 in common, so we can pull out a -4 there. So if we factor out a -4 from -4x, you're left with positive x. And we pull out a -4 from -8, we're left with plus 2. Close that parentheses and close that main parentheses. So factor by grouping works. Then what's left inside the parentheses after you pulled out what they had in common should be the same, or you should have been able to manipulate it to be the same. And we did. And so we can pull out inside. This x plus 2 is what they both have in common. So we're going to pull out an x plus 2. We're going to pull out that whole parentheses from both of these groupings. So if we pull out an x plus 2, from the first grouping, you're left with just an x squared. And when we pulled out x plus 2 from the second grouping, we're left with a -4. I should have put it in here the whole time. This was all equal to 0. We're trying to find when this was equal to 0. Not quite done, still can be factored more. I noticed that x squared minus 4 is a difference of squares. I'm okay, x plus 2 It can't be factored any further. Okay, so we have 3x cubed. Something's going on weird with my, it's letting me, well, maybe not. All times x plus 2. It's bizarre because when I'm hovering over it, it's writing, which has never done that before. So let me, if I get out of here and then go back into it, I probably won't have that problem anymore, I hope. Okay, so we're looking at when we have 3x cubed, all times x plus 2, all times x minus 2, all times x plus 2. Eeks. And it is still doing it. Okay, so problems with my pen, and I'm still having problems. Let's see if we can do it still. So we're still looking for x-intercepts. We just factored our whole polynomial as far as possible. Now we can set each factor equal to 0, and we can find our x-intercepts. So looking at when is 3x cubed equal to 0, that's when x equals 0. Shoot. When is x plus 2 equal to 0? That is when x is equal to negative 2. X plus 2 equals 0 when x x equals 2. And x plus 2 is 0 when x is equal to negative 2. Okay, still not working, and I don't like it. Okay, so I finally figured it out or fixed my problem, and so we just found our x-intercepts. Notice that we have two factors here of x plus 2 and x plus 2. X minus 2, usually you don't write that twice. This is x equals negative 2, has a multiplicity of 2. And so because it's an even multiplicity, then we know that it's going to touch the x-axis at negative 2. The other intercepts, 0 and positive 2, they're multiplicity 1, so we know we're going to cross the x-axis at those values. Okay, so we can kind of put together what we've got. Plotting our x-intercepts. We have negative 2, we have 0, and we have positive 2. There's one thing that might help us here. I'm looking at this and just seeing that I have an x-intercept at negative 2 and positive 2. Maybe, just maybe, I think maybe, I'm not sure. I was thinking maybe this was symmetrical. And I don't think it is. Now that I look back at the equation, if I plug in negative x wherever I see an x, that's going to change my equation. Multiplying through by negative is going to change. Yeah, so it's not going to work. We saw that it's going to be shooting upwards in both cases. we saw that x equals -2. It actually just touched the x-axis there. And so we're going to have to come down, touch the x-axis, turn around. And then I have to turn around so I can cross the x-axis at the origin. And then I have to go below the x-axis and come back around. I don't know where exactly, and cross at x equals +2. Okay. So that is 5.2. 5.3 and 5.4 are graphing rational functions. So graphing rational functions. And I'm going to just kind of put them together when I talk about them. Let's see how they... Okay, so a rational function. What is a rational function? Basically, a rational function is in the form where you have r of x is equal to p of x all over q of x, where p of x is a polynomial and q of x is a polynomial. So we noticed that when we had rational equations, that we couldn't have any value which set our denominator equal to 0. And so for our domain, that's all values of x such that x does not set q of x equal to 0. So domain of r of x are all real numbers x such that q of x does not equal 0. Okay, so those values which set that denominator equal 0 are kind of important values and will help us determine what's going on with our graph. So we have vertical asymptotes. So let's first look at what a vertical asymptote really is saying. Basically, it's saying as x is approaching some particular number, not infinity or negative infinity, as x is approaching that number, your y value is either going to positive infinity or negative infinity, but it's never going to touch or cross. So as x, and I'm going to write it kind of in mathematical terms on how you would see it like we were writing it before for the end behaviors of our graph. So as x approaches some value, let's call it c, then f of x, your y value, goes to either positive or negative infinity. when I'm saying when it's approaching x, the value x, usually we think about it as approaching it from the left, but really here we're going to think about approaching both directions. So as your x value, as you get closer, as you get closer and closer to x from the left, y goes to positive or negative infinity. And as x gets closer, as you get closer and closer to x equals c from the left, y goes to plus or minus infinity, and as x gets closer and closer to c from the right, y goes to positive or negative infinity. When we're looking at vertical asymptotes on the graph, when you graph it, you normally won't see this line, but we put in this line to kind of help us graph it. And so when we're drawing asymptotes, we usually denote the asymptotes with a dotted line. Vertical line here, x equals c. We were saying was a vertical asymptote. So what's going to be happening is, as your graph comes in closer and closer to that x value of c, it's either going to be blowing up, going to positive infinity. It could have been coming down and shooting down to negative infinity. It's not going to do both. It's either going to do one or the other. So here's an example as x is getting closer and closer to c from the left-hand side of c. It goes to positive infinity. And as x is approaching c, maybe from the right-hand side, it also could be going upwards. So there's an example. So technically, and just so you'll see this in the future, x, that's telling you where your x value is going. Before we were looking at negative and positive infinity. Now we're talking about c. X is going towards c. This minus right here that I'm putting, that looks kind of like an exponent, this is telling me which side I'm approaching from. I'm approaching the left of a number. Think of it, has the negatives on the negative side. So approaching on the left. I am doing this with my equation f of x. This is going to equal, in this case, positive infinity. If I look at the limit as x is approaching on the right, I would write that with a positive. Kind of looks like an exponent, but not. So it's x arrow c, and if I have a positive looking exponent, that's telling me I'm looking at what's happening as we're going on the right-hand side. But the vertical asymptotes could be going opposite direction. I mean that things could have been going opposite direction. One can be going up, one could be going down. So for instance, we could have been coming down like this, maybe coming up like this. So notice as x is approaching c on the left, you're going down to negative infinity. And as x is approaching c from the right, we're going up to positive infinity. basically what you need to know as you're approaching some x value, some vertical line going through some x value, and if the graph shoots upwards and downwards as you approach it, that's a vertical asymptote. These vertical asymptotes, we can find them. So vertical asymptotes occur at values which set the denominator equal to 0 but not also the numerator. If it sets both the numerator and denominator equals 0, well, it's still undefined because you can't have any value which sets the denominator equals 0. But what's happening there is that you have an open circle instead of an asymptote. So if some value sets both the numerator and denominator, equal to 0, then there is no vertical asymptote. And you have an open circle. At that point. It's not defined on our graph for f of x. So basically, because it's setting both the numerator and denominator equal to 0, that's telling me that both the numerator and denominator have a factor that are the same. And so if we cross both of those factors out that they had the same, and we plug then back the number that set them both equal to 0 into what the simplified version, that should give you some y value. And that's where the point of your open circle will be. So for example, let's say you were given r of x. This is equal to x all over x to the 4th minus 1. So if it says find the domain of r of x, okay, so again, domain, we're looking at problem spots. So real numbers that we can plug in and we would not get back a real number, or it's undefined. And so we're going to have problems when our denominator is equal to 0. We cannot have x to the 4th minus 1 cannot equal 0. So I can approach this a couple different ways. I can isolate x to the 4th and take the 4th root of both sides. Or I can factor this. This is like a difference of squares. This is the same thing as x squared minus 1 all times x squared plus 1. X squared minus 1 factors a little further. This is x minus 1 times x plus 1. X squared plus 1, that's not factorable over the real numbers. And so we're going to leave it as x squared plus 1. So x minus 1 can't be 0, x plus 1 can't be 0, x squared plus 1 is never 0 for a real number. It's an imaginary root. So x can't be 1, or x cannot be negative 1. So our domain are all real numbers except for that. If I put that in interval notation, I'm going from negative infinity up till I hit negative 1, parentheses. I'm using all the numbers between negative 1 and 1, not including, so I have parentheses. And then I'm looking at all the numbers from 1, not including, to infinity. So find the vertical asymptotes. Okay, so these are numbers that set the denominator equal to 0, but not also the numerator. So numbers that set x to the 4th minus 1 equal to 0, but not also our numerator, x equals 0. Well, they don't. There's none of the numbers that set my denominator equals 0, which are negative 1 and 1. My numerator is equal to 0, well, when x is 0. And so, since they are not the same, I know I have vertical asymptotes, both at positive 1 and negative 1. Okay, so don't just give the number, because these are actually equations. And it's a vertical line. So equations for vertical lines are in the form x equals. And so our vertical asymptote is going to occur at x equals negative 1 and x equals 1. Maybe one more. So if we had r of x is equal to 3 times that quantity x squared minus x minus 6 all over 5 times x squared minus 4. 5 times the quantity x squared minus 4. So you should be able to find the domain. So our denominator can't equal 0. I can see that x squared minus 4 factors, it's a difference of squares as x minus 2, x plus 2. So x can't be 2, or x can't be negative 2. Vertical asymptotes, I have to be careful. I need to make sure that doesn't set my denominator also equal to 0. So sometimes it's just helpful to factor, and it will be helpful when we start graphing these to factor the numerator. So if we factor the numerator, so two numbers that multiply to -6 add to -1, so -3 and +2. So x plus 2, x minus 3. The 3 out front, all over 5, that factored as x minus 2 times x plus 2. So notice that x equals -2 sets both the numerator and denominator equal to 0. And so x equals -2 is an open circle. On the graph of R of x. Where if I look at +2, +2 sets my denominator equals 0, but it doesn't set my numerator equal to 0. And so x equals +2, which is a vertical line, is a vertical asymptote. So to find that point where it's an open circle, well, basically, if we just simplify this and cancel out our x plus 2's, x still can't be -2 because that's not our original function. But simplifying it, we would have then R of x is equal to 3 all times. We'll have a factor of x minus 3 on top, all over 5 times x minus 2 on the bottom. And now if we go in and we plug in -2 wherever we see an x in here. So I'm going to just go in and put parentheses wherever I see x. We have 3 parentheses, another parentheses, -3 in my parentheses, all over 5 parentheses. I see an x, put parentheses -2. So this was when x was -2. So replace -2 with x, or x for -2, or put it in the parentheses. So reducing, order of operations, inside parentheses first, -2 minus 3, that's a -5. All over 5 times, well, -2 minus 2 is -4. 3 times well, I guess I can reduce. 5s and 5s cancel, so I have 3 times -1, or negative over negative. This is going to be positive 3/4. So we have an open circle at the point -2, and our y value will be 3/4. Okay, so thank you for bearing with me. So let's stop here.